Hello, I welcome you all in this course on steam and gas power systems. In this session, we will solve certain numericals, but before we start solving numericals, I must tell you that the gas turbines are, we have amply discussed open type of gas turbine, open cycle gas turbines. There are closed cycle gas turbines also, and they are semi-closed type also or semi-open. Now, in open type of gas turbines, the compressor sucks air from the surroundings and this air participates in combustion in the combustion chamber. Hot gases, hot flue gases emerging from the combustion chamber, they go to the turbine, expansion takes place, output is attained and the exhaust of the turbine is sent to the atmosphere or used for regeneration. In closed cycle gas turbines, the entire circuit is closed. It means if we start from this temperature entropy diagram, state 1, 2, 3 and 4, the entire circuit is a closed cycle. No fresh air is sucked into the system. In the combustion chamber, the air is used other than the air in the cycle. Outside air is used for burning the fuel. In this case, in such type of systems, we can use low grade type of fuel also, and the entire system can work on relatively high pressure. This pressure at state 1 need not to be atmospheric pressure. It can be, let us say, 2 bar or 200 kilopascal. So, the entire cycle will shift in upward direction and it is going to be for the same output we can have a compact cycle. It has certain advantages and disadvantages. First advantage is because the cycle can operate on high pressure side. So, the thermal efficiency is high or we can design a cycle for high thermal efficiency. When thermal efficiency high, it means for the same power output the size of the plant will reduce. So, smaller size, either we can say thermal efficiency is high. If we are maintaining the same output, then we can go for a smaller turbine. For this closed cycle gas turbine, part load efficiency is also very good. I mean, it is better than the open cycle gas turbine. If you compare the part load efficiency, it is the efficiency and the load. Every power generating machine is designed for a particular load, right? At a particular load, the efficiency may be high, but the moment you change the load, efficiency may not, the reduction in efficiency may not be significant, right? But in turbo machines, this happens in reciprocating machines like IC engines, 2-stroke or 4-stroke engines. But in turbo machines, this curve is like this. It is almost vertical. So, the moment you deviate from the design condition, the deterioration in efficiency is very fast. But if you compare this is known as off design performance. But if you compare the off design performance of closed cycle gas turbine and open cycle gas turbine, the off design performance of closed cycle gas turbine is better than that of open cycle gas turbine. And because the cycle is closed, so working medium is not lost, there is no loss in working medium, right? For burning the fuel in the combustion chamber, external air is used. Reynolds number are high, I mean during the cycle, right? And in this cycle, no contamination takes place. So, due to contamination, the loss in energy due to contamination, that is also avoided in closed cycle, in the closed cycle gas turbines. And of course, we can use inexpensive fuel for closed cycle gas turbines. There are certain disadvantages also. Disadvantage is it is a dependent system, because cooling from process state 4 to state 1 has to be done in a condenser. So, it is a dependent system. It is a I mean, it is a complex system also. It is not as simple as the open cycle gas turbine. It is a complex system, and cost wise also the cost of closed cycle gas turbines is high. Right. Now, after this we will solve certain numericals on gas turbines. This is the first one, which states that a gas turbine plant consists of one turbine for compressor drive and another for output, and both are having their own combustion chambers which are served by air directly from compressor. Air enters the compressor at 100 kilopascal and 15 degree centigrade and is compressed with isentropic efficiency 0.76. So, let us start drawing the temperature cycle on temperature entropy diagram. Temperature entropy diagram. So, state 1 to state 2, and it has certain isentropic efficiency. So, definitely the compression is not isentropic. So, you will be getting 2 dash. Air enters the compressor at 100 kilopascal. So, P1 is equal to, here we will write 100 kilopascal, and T1 is 15. So, 15 plus 273, 288 Kelvin. Isentropic efficiency is 0.76. 0.76. Gas inlet temperature and pressure in both turbines are 680 degree centigrade. So, this is gas inlet temperature, this is T3, and T3 is 680 degree centigrade plus 273 is going to be 953 Kelvin, or right here. T3 is equal to 680 plus 273 is equal to 953 Kelvin. And 500 kilopascal. So, P2 is 500 kilopascal. The isentropic efficiency of the turbine is 86%. So, isentropic is 0.86. This is isentropic efficiency of the compressor. The mass flow rate of air at the compressor inlet is 23 kg per second. Mass flow rate is 23 kg per second. The calorific value of fuel is 42 megajoules per kg. So, CV is 42 megajoules per kg. Calculate the output of the plant and thermal efficiency assuming Cp, and for air Cp is equal to 1.005 kilojoules per kg Kelvin, and gamma is 1.4 for air, and Cp for gases is different. So, this is Cp for air, Cp for gas is 1.128 kilojoules per kg Kelvin, and gamma is 1.34. So, these are the data available with us. Cycle is this, and the particular thing about this numerical is that it has two turbines. Both are having their own combustion chambers which are served by the air directly from the compressor. So, compressor air is divided in two parts. It goes in two different combustion chambers, and combustion takes place. The gas inlet temperature and pressure in both turbines is also same. So, we will start with finding out the temperatures at sealing points T4, because it has also certain efficiency. This is T4 dash. So, the numericals related with the gas turbines, first thing you should do, you should try to find temperatures at all the places. Once you have the value of temperatures, a specific heat is normally given. If in the numerical the specific heat of gas is not given, you can take a specific heat of the air, and that is how you can find the total energy or enthalpy in that place, and enthalpy difference can be calculated, right. So, first of all, because we will find the temperature of air at state 2. So, 2 dash. So, T2 by T1 is equal to P2 by P1 raised to power gamma minus 1 over gamma. So, gamma is 1.4. So, gamma minus 1 by 4, gamma 1.4 minus 1.4, it is 0.4 by 1.4, 1.3.5, 0.286. So, directly we can use 0.286 instead of writing this. So, T2 is equal to T1 is 288, P2 by P1. Now, P2 is 500, P1 is 100 raised to power 0.286, and this gives the value of T2 as 456.34 Kelvin. Right. Now, once we have the value of T2 we can write here T2 is equal to 456.34 Kelvin. Again, once we have the value of T2, then T2 minus T1 divided by T2 dash minus T1 is equal to efficiency 0.76. Now, T2 dash is equal to T1 plus T2 minus T1 divided by this 0.76, this is efficiency of the compressor, right, and then T1 is 288 plus T2 is, we have calculated 456.34 minus 288 divided by 0.76, and this gives the value of T2 dash as 509.5 Kelvin. So, T2 dash is equal to 509.5 Kelvin. Now, we have the value of T2, we have the value of T2 dash. Now, T3 is 953 Kelvin, it is already with us. Now, T3 is with us, we can easily find the value of T4, because all these values will be required later on. So, T3 by T4 is equal to P2 by P1 raised to power 0.286. Instead of writing gamma minus 1 over gamma, I am writing 0.286. Now, T4 is T3 divided by P2 by P1. So, T3 is equal to how much? 953. So, we will directly write 953 Kelvin, and P2 by P1 is 500 by 100, 5 raised to power 0.286, and this gives the value of T4 as 633.56 Kelvin. So, T4 633.56 Kelvin. Okay. Now, T4 dash. So, T3 minus T4 dash divided by T3 minus T4 is efficiency of the turbine. Efficiency of the turbine is given here. It is 0.86. So, T4 dash is equal to T3 minus efficiency of the turbine T3 minus T4, and that is T3 is 953 Kelvin. So, 953 minus 0.86, 953 minus T4 is 633.56, and this gives the value of T4 dash is 678.28 Kelvin. So, T4 dash is 678.28 Kelvin. Now, we have temperatures at all salient points, right. Now, after this we will calculate work consumed by the compressor, because compressor is providing air for both the turbines, and each turbine is having its own combustion chamber. So, work of the compressor is Cp T2 dash minus T1, right. Now T2 dash is 509.5, so 1.005, 509.5 minus T1 is 288, right. So work of the compressor is 222.6 kilojoules per kg. This is work of the compressor. Now work of the turbine, each turbine, because both the turbines are having the maximum temperature, right. So work of per kg work for each turbine is same. If you change the mass flow rate, then definitely we are going to have different work output. So per kg of gas work output is, turbine is CPG, this is CPA, T3 minus T4 dash. CPG is given here 1.128, T3 is 953, and T4 dash is T4 dash right now, oh yes, 678.2, and then work of the turbine is 309.88 kilojoules per kg. Now this turbine is used for running this compressor. So this is specific work output. So mass of the air in compressor is equal to mass of the gas multiplied by specific work of the turbine. Now if we have to find the ratio of gas and air, then mass of the gas divided by mass of the air, right, is equal to work of the compressor divided by the work of the turbine. Work of the compressor we already calculated 222.6 kilojoules per kg, right. Work of the turbine is 309.88 or 309.9. So the ratio of mass of the gas and mass of the air is 0.7183 kg. It means this ratio is existing for, so if we are using 1 kg of air, 1 kg of air, now it means the 1 kg of air which is sucked into the compressor is burned in the combustion chamber, right. Some mass of the fuel is added, suppose X mass of fuel is added. So 1 plus X, out of that this much of flue gases are used in one turbine to meet the energy spent in compressing the gas. Now this 1 kg of air plus X kg of fuel minus this will give the output, will be used for output turbine, not give the output, it will be used for output turbine. So now mathematically we can write, so this mg by ma will write somewhere, mg by ma is equal to 0.7183, because we will be requiring this information later on. Now ma plus mf, mass of the air plus mass of the fuel burned here, H3 minus ma H2 dash, combined in for both the turbines. We have considered this mf for both the combustion chambers, right, is equal to mass of the fuel into calorific value of the fuel, right. And if you are using ma is 1, because we want to find how much fuel is burned for 1 kg of air. So if we take 1 kg of air, then mf H3 minus H2 dash is equal to mf CV, right. Now H3 again 1 plus mf CPG T3 minus CPA T2 dash is equal to mf into 42,000, because the calorific value is given in megajoules. So, this megajoules has to be converted into the kilojoules because we are dealing in kilojoules. Now, T3 is with us, T3 is 953 Kelvin, CPG is also with us 1.128, CPA specific heat of air is 1.005, T2 dash we have already calculated 509.5 Kelvin. Now, the only unknown is mass of the fuel. So, mass of the fuel we will getting here from here, we will be getting the mass of the fuel as 0.01375 kg of fuel per kg of air. Mass of the fuel, this much of mass of the fuel is used for 1 kg of air. It means the total mass of the flue gases is 1 plus mf, that is 1 plus 1.01375. This is the total mass kgs per kg of air. This is the total mass of the flue gases if we are compressing 1 kg of air, right. But out of this, this is used for running the turbine which is driving the compressor. So, difference of these two mass of flue gases will be available for power generation. So, minus 0.7183 will be used for output. So, MO is equal to 0.2954 kg per kg of air. Is it clear? First of all, we have calculated how much mass of the fuel will be burned for 1 kg of air. Part of these flue gases, this much is used for running the turbine which is driving the compressor. Rest of the flue gases will be used for power generation. So, this is the amount of flue gases which are available for the power generation when 1 kg of air is in circulation. So, power output is going to be 0.2954. Now, the mass of the air circulated is 23 kgs per second into 23 into work output of the turbine. So, work output of the turbine is 309.88. We have calculated earlier. Work output of the turbine. So, power output is 2105.38 kilowatt, right. And thermal efficiency is equal to power output 2105.38 divided by the heat supplied. The heat supplied is 1.01375. This is the mass of the fuel burned. Here we will use only mass of the fuel burned and the calorific value of the fuel. This is the amount of heat liberated. If we take this ratio multiplied by 100, and that will give 15.85%. That is the thermal efficiency of the system. Okay. Now, after this, we will take up another numerical which is based on reheat cycle. Now, I will read the problem statement that states, in a compound gas turbine, air from compressor passes through heat exchanger for regeneration heated by the exhaust gases from the low pressure turbine and then into high pressure combustion chamber. The exhaust gases from high pressure turbine passes through a low pressure combustion chamber to a low pressure turbine which is coupled to the external load. It means this problem, there is reheat and regeneration, right. So, if we draw this temperature entropy diagram, for every problem this temperature entropy diagram has to be drawn. So, now state 1 to state 2, and this efficiency also, this HP and LP turbines are 0.86 and 0.4 and 0.8 respectively. Okay. So, this has certain efficiency we will get 2 dash. So, isentropic efficiency of compressor, HP turbine, LB turbine are given 0.86, 0.84 and 0.8 respectively. The mechanical efficiency is also given, right. So, output will always be multiplied by the mechanical efficiency, that is the actual output we will be getting, right. So, mechanical efficiency is the output available at the rotor shaft divided by the output generated in the turbine. So, turbine output and output available at the rotor shaft, that ratio will give us the mechanical efficiency, that is 0.92. In the heat exchanger 75% heat is available. So, effectiveness is 75%. The temperature of gas entering HP and LP turbines is 600, and this temperature is different, 600 and 625 degrees centigrade respectively. The atmospheric temperature and pressure 15 and 100 kilopascal. Cp for air and gas both are same, compression ratio 4. So, single compression ratio, so P2 by P1, P2 by P1 is equal to 4. Now, air is heated up to this point 3, sorry, this is 3 we will get from regeneration. So, we will write 4. So, it is 4, from 4 it is expanded to 5, again this is 5 dash, then from 5 dash to 6, sorry, 5 to 5 dash, and then it is again reheated state 6 and 6 to 7 and then 7 dash. Okay, and after 7 this it should be heated up to 3, this is T3 state 3, but it is heated up to T3 dash only. Ideal temperature is 3 if the regeneration is perfect, but since regeneration has certain effectiveness, it is only 0.75, so it will go up to 3 dash only. Now, this is the temperature entropy diagram for entire process. Now, first of all, as we have done earlier in earlier numericals, we will find the temperature at all the states. So, T2, quickly we will go for this, T2 is equal to 288 4 raised to power 0.286. Here 0.286 is again gamma minus 1 over gamma, that is 1.4 minus 1 divided by 1.4, 0.4 divided by 1.4, 1.3.5 and 0.286. Okay. So, this gives T2 is equal to 428 Kelvin. Now, again T2 minus T1 divided by T2 dash minus T1 is equal to the efficiency of compressor is 0.86. Efficiency of the compressor is 0.86, right. Now, T2 is with us, T2 dash is not known. From here we will get the T2 dash, and the T2 dash is 450.79 Kelvin or 450.8 Kelvin, right. And it is easy to do. I mean, we know the value of T2, we know the value of T1, and this is known to us, and we can find the value of T2 dash. Now, one turbine is used for running the compressor, T4 minus T5 dash. So, T4 minus T5 dash Cp, right, and is used to run the compressor Cp T2 dash minus T1. But here this is the turbine output and compressor is coupled with the shaft. So, turbine output has, now again it has mechanical efficiency of 92%, 0.92. So, this will be multiplied by mechanical efficiency. So, 0.92, 1.005 because it is same for both the cases. T4 is how much? It is given here maximum temperature T4 is 600 degrees centigrade. So, 873 Kelvin minus T5 dash is equal to 1.005 multiplied by T2 dash is 450.79 minus 288. From here we will get the value of T5 dash. So, T5 dash is 756.05 Kelvin. Now, we have, but we do not know the pressure at this 5 Px. This Px is not known to us, but we know the HP turbine isentropic efficiency. HP turbine is 0.84, that is T4 minus T5 dash divided by T4 minus T5. Now, here we have the value of T4, we have the value of T5 dash, we can find the value of T5. Now, the T5 is 722.35 Kelvin. Once we have the value of T5, we have the value of T4, then T4 by T5 is equal to P2 by Px raised to power gamma minus 1 over gamma. Right. Now, gamma minus 1 over gamma is known to us, P2 we know, it is P2 by P1 is 4. So, and P1 is 100 kilopascal, it is given here, P1 is 100 kilopascal. So, P2 is 400 kilopascal, right. Now, from here, because T4 and T5 are also known to us, we can find the value of Px, and the Px is 163.9 kilopascal. Now, here we have the value of pressure and temperature here, and this is 7 dash, right. Now, we can find the value of T7, because T6 by T7 again is equal to Px by P1 raised to power gamma minus 1 over gamma. Now, we have the value of T6, T6 is 625 plus 273 is equal to 898 Kelvin, 898 Kelvin, right. So, T6 is with us, T7 we have to find out, Px is with us, P1 with us, and this is also with us, you know all these values. So, T7 is 779.7 Kelvin, right. Once we have the value of T7, we can easily calculate the value of T7 dash. T7 dash minus T6 divided by T7 minus T6 is equal to isentropic efficiency of low pressure turbine, that is 0.8. Now, from here we will get the value of T7 because other values are known. So, T7 dash is coming 803.33 Kelvin. Now, we have temperatures at all salient points, and we can calculate the energy interaction. One thing is remaining, that temperature at 3 dash, because this temperature will be required to find how much heat is added in this process. So, effective nature of regeneration is given, that is 0.75, and that is equal to T3 dash minus T2 dash divided by T7 dash minus T2 dash. T7 dash, this is the temperature of exhaust gases, and this is the exhaust of the compressor. This is the maximum possible temperature difference or maximum possible heat transfer, and this is actual, right. So, here these values are known, this is known, T3 dash we can get from here, and T3 dash is 715.19 Kelvin. Now, we have temperatures at all salient points, right. Now, heat transfer Q per kg of air is equal to Cp T4 minus T3 dash plus Cp T6 minus T5 dash. This is the amount of heat transfer. We have the value of all these values with us. This will give us a heat transfer of 361.56 kilojoules per kg. Right? We will be putting T4, T3 dash, T6, T5 dash from here, and we will be getting, this is the amount of heat liberated by burning the fuel in cumulatively in these two processes, main heating in combustion chamber and then reheating in another combustion chamber. And work output is Cp T6 minus T7 dash, right? And we have the value of T6 and T7 also, and this will give the work output as 95.14 kilojoules per kg, right? And then we will take the ratio W by Q, and W by Q multiplied by 100 will give us the thermal efficiency, and which is 26.31%, right? So, this numerical involved the reheating in the cycle and as well as regeneration in the cycle. That is all for today. From the next class, we will start with centrifugal compressors.